Hello, everybody. Welcome to our first seminar of the new semester at the Institute of Astrophysics. Today we have with us Konstantinos Migkas. Kostas did his undergrad degree from the physics department at Aristotle University of Thessaloniki, and his PhD at the University of Bonn. His thesis work was on the isotropy of the universe, or lack thereof, for which he received awards, accolades. He received an offer to continue his postdoctoral career as an ESA research fellow, but instead he chose to accept the Ord Fellow at Leiden, where he's now. And today he will talk to us about said isotropy of the universe. And without further ado, Kostas, the floor is yours.
Thank you very much, Vaso. Hi, everyone. As Vaso said, I'm Kostas. And before I start, I really want to thank Vasilis, Vaso, Kostas, Sifis, everyone here for the hospitality and for the invitation. It's really nice to be here. I've never been to Iraqion for more than a day in the past, so I have the time to explore a little bit, and it's fantastic. And yeah, today I will talk to you about my main research interest, which is how we can probe cosmic isotropy using galaxy clusters, which is a relatively new method, what we already know and what we will try to learn in the next few years. But before I start, yes? In Zoom. I think so, but let me check. Maybe not. Yeah, okay. Now you should be able to see it.
Yes.
Okay, great. Let me put also the timer so I don't talk to you for more than an hour.
Are you see, are we looking at the presenters view?
Yeah, also we see the presenter.
Okay, right. So I'll just go to the PDF.
No, just receive the presentation of the PowerPoint and then share.
Okay. Sorry, should I?
Stop sharing.
Okay, just a second. Yeah.
Now start the presentation.
Right.
And then share.
And yeah, doesn't let me. Okay.
It should be not another window, but another screen.
I have. Okay, wait. I'll just use the PDF. It makes no difference. But it's the same. I don't have any animations or anything, so it should be fine.
Okay.
Now it should be better, right? Yeah. Okay. Yeah.
There's some way of
It will go away.
Okay, yeah. I mean, I don't think it will hide anything there, so we should be good. So before I dive into cosmic anisotropies, I just want to give you a very brief overview of what I do in general, because I do other things as well, and maybe one of you is interested in one of these things, so we can also discuss about other stuff. So, for example, earlier this year, we published a paper on Eero-zeta and the cross-calibration with Chandra and XMM using cluster-scaling relations. So if you are interested in Eero-zeta, come talk to me. We also have, in collaboration, in the SPT collaboration review, a paper that we are going to publish soon about the X-ray and weak lensing analysis of a very high redshift merging, colliding cluster system, which is quite interesting. There is a special gas bridge in between, a shock front. It's the first such system ever discovered. We also we are writing the paper now. We have the second ever detection of a cosmic filament through its X-ray thermal emission using Suzaku and XMM data. The first ever was also this year, also from our group, with my collaborators from Bonn. So it signals, let's say, the start of a new era where we can detect cosmic filaments from and measure their temperature and the gas density, and not just from emission lines. And also, I have a set for publication review, my first review on cosmic isotropy tests with clusters, which will also serve a little bit as a guide for non-experts if they want to just grab our data and play around, what they should be careful of, what they should avoid, and how to interpret the data to derive cosmological parameters. So if you do anything similar to that and you want to discuss, I'm very happy to do so. But let's move on to my main research activity, which is testing the cosmic isotropy with galaxy clusters. And before I show you the results, I'll just say a few words about the general framework of what's going on. So as you know, isotropy is something extremely important as an assumption in our everyday extragalactic research. It's taken for granted so much actually that we start to believe sometimes that it's a well-known, proven fact, which is not. It's mostly an assumption for the low redshift universe still. And the strongest evidence we have for isotropy comes from the very high redshift universe, from radiation, from the CMB, which has a rest frame in which the radiation of the early universe is extremely isotropic, impressively isotropic. And now the core assumption of isotropy is that the low redshift universe, the matter in the low redshift, galaxies, clusters, supernovae, share the same rest frame as the radiation in the very early universe. That's the core assumption, right? That the CMB rest frame and the low redshift matter frame are the same. Now, when the cosmological principle alone doesn't tell us the scale at which matter should converge to isotropy within the CMB rest frame. For this, we need a model. Different models give you different scales for the convergence to isotropy. So in essence, when we test cosmic isotropy with our data, we don't test the cosmological principle itself. We test a model which gives you a prediction of the scale at which we should see this thing. For example, if I show you that at 500 megaparsecs, we don't see convergence to isotropy, it doesn't mean the cosmological principle is invalid. It means that the prediction of the scale of lambda CDM might be invalid, and maybe another model describes the local universe better. So that's what we do. Now, the cosmic isotropy assumption boils down the local universe in two things. First of all, we should measure the same expansion rate towards every direction, the same Hubble constant. And we should not see any major matter bulk flows. If you're not familiar with what a bulk flow is, don't worry, we'll talk about them in detail. So these two things are still to be shown in the local universe. Most studies show the opposite, actually. Nevertheless, we don't have yet strong enough evidence to debunk, let's say, the scale of lambda CDM, the scale in which lambda CDM predicts isotropy. So it's extremely crucial to keep testing observationally with new methodologies, new data, new everything to fully understand what's going on. And if we should alter our model of the local universe. In my biased opinion, at least, galaxy clusters are the best probe to do that for two main reasons. First of all, they cover a redshift range from the local universe up to redshift 1 or 2, but we have thousands of clusters up to 0.5 redshift, which corresponds roughly to 2 gigaparsecs. And they are the only probe that can trace the redshift distance relation while they cover the full sky uniformly up to these redshifts. For example, supernovae samples do not cover the full sky. They have huge empty regions where we don't have any data. And galaxy surveys, which do cover the whole sky, they don't go up to 0.5. So galaxy clusters are the only probe that allow us to test this thing up to 2 gigaparsecs or so, for now at least. And the other big strength of galaxy clusters is that each cluster can give you cosmological information in many different ways. For example, for one cluster, we can take X-ray measurements, like we can measure the X-ray luminosity, the gas mass, the effective radius, right? In microwave, we can measure the Compton parameter, which corresponds to the total pressure of the gas. In infrared, we can measure the luminosity of the galaxies in there. And all that quantities, we need to know the distance to derive them. But we don't know the distance to the clusters, so we have to infer it from the redshift. So we measure the redshift, we assume some cosmological parameters, we get the distance, we use this distance to measure, to estimate these cluster properties. This means that all these cluster properties are cosmology dependent, and that's the take-home message from here. So one cluster can give you information about its distance in 3, 4, 5 ways. Some of them completely independent, some of them correlated.
How would you frame as a cluster?
Well, in X-rays, it's very obvious. There is a huge gas overdensity, which you can see as an excess in X-ray emission. And they are like black dots in a white canvas there. In optical, you can define them as overdensities of galaxies. But in X-rays, they stand out. Right. So all these cluster properties, they scale with cluster mass, right? And they scale with each other as a result. So they give rise to so-called cluster scaling relations, which are theoretically motivated. They are easy to understand why they are there, and they have been established observationally for more than 2 decades now. And they are usually simple power laws, simple single power laws that describe these relations. And you can think of a cluster, you can think of another cluster with a higher mass. This means it will also be bigger, so larger radii, larger radius. It will also have more protons, more electrons in the gas, so more interactions, more X-ray photons, higher luminosity. And also higher mass means deeper gravitational well, higher kinetic energies of the gas, higher temperature. As a result, when you have a higher temperature, you will also have higher luminosity, and that's your luminosity temperature scaling relation. The key cluster quantity that we want to have is the X-ray temperature if we want to test cosmic isotropy. And why? Because we can simply take our telescope, extract a spectrum of a galaxy cluster, its gas, fit the appropriate thermal emission models, and these emission models are very sensitive to the temperature, as you can see here, especially at the high energy part. So from that, we can easily estimate the temperature of the gas, and through this process, cosmology enters nowhere. So even if we live in an Einstein de Sitter universe or in an anisotropic universe with H0 10 and 100 to the other side, you will measure the same cluster temperature, whatever you do. What we can do now is exploit the scaling relations between the cosmology independent temperature and cosmology dependent quantities. For example, the luminosity, right? Have the luminosity temperature relation. We can decompose it into observables on one side. For example, we have the flux, we have the temperature, we have the slope, which is cosmology insensitive. It has H0 has no impact on the slope. And on the other side, we have a bunch of cosmological parameters. We have H0, A, we'll say in a bit what it is. We have omega matter, we have W, and we have the redshift. The redshift is a combination of observables and cosmology, as you'll see. Now, in local samples below 0.3 redshift, omega matter and W are quite irrelevant because also they enter through the redshift evolution and their contribution kind of cancels out. So even if we have omega matter 0.2 or 0.4, our scaling relation won't change significantly. So what we can do is measure this, and the redshift, and we can determine, we can put absolute constraints on this sum 2 times log H0 for the luminosity plus the normalization, which is A. Scanning the sky, taking 50 clusters there, 50 clusters there, 100 clusters there, we can see if this sum varies across the sky, right? Now, H0 and A are completely degenerate, so we cannot tell if any observed difference comes from one or the other. It's the normalization of the scaling relation. It's yeah.
So it's this power law that you showed us, it's the normalization.
Exactly.
At some luminosity or at some.
Exactly. At some temperature. Yeah. Exactly. Exactly. Yes. Now, A is a quality that has to do with internal cluster physics. It connects the luminosity of the cluster to the temperature of the cluster, or the gas mass to something else, to the pressure, for example. It has to do with thermodynamics, with baryonic physics at scales of 500 kiloparsecs or so. So it's irrelevant for cosmology. We can assume that baryonic physics and thermodynamics do not change with direction. And if we assume that, A should not depend on the direction. It's an internal cluster property that has nothing to do with the distance between us and the cluster. So again, constraining the absolute variation of this and assuming that thermodynamics are the same towards different directions, all the variation can be attributed to H0 as an example. So we can actually measure the relative change of H0 in the sky. We have to be careful. We cannot put absolute constraints of H0 because we have to assume a value for that. We don't know if H0 is 100 or 20, but we do know if it changes by -5% or +10%.
Sorry, I ask.
Yeah.
So when you decompose the left part of the first equation into these two components, is this, is there a good physical motivation on why you get this functional relation, or is this model dependent?
This is model dependent in an FRW universe, but it's rather irrelevant. You can model it any way you like. So this is just the luminosity, just the flux times the distance squared. From the distance in FRW, you have this integral from 0 to redshift, where you have omega matter and W, and also you have the redshift evolution, which we pretty much know, which you also have omega matter and W. You can choose a cosmographic approach where you don't have these parameters, and you just have different orders in the distance, approximation orders, where you just see the kinematics. But whatever has to do with orders of redshift squared and stuff will be vanished for low redshift samples. If you go at high redshifts, 0.6, 0.7, these are not irrelevant. So then any apparent variation of this observable can be attributed to this as well. But there are ways to disentangle them. They are quite simple because they have different effects at different redshifts. So it's not an absolute degeneracy of any kind.
So you assume that A or B doesn't have any variation at all, which is an assumption. You argue that doesn't have big variations.
Yes.
Without knowing.
We do allow noise. We do allow noise because out of pure luck, some clusters might have different physical effects than others. So we do allow noise. We don't fix it to an absolute value, and that's it. Because then
I presume changes that you expect in H0 are small. Right?
yes, right. But no, you can't. But the assumption is that if thermodynamics local scales are the same, right and left, then this on average, if we have 200 clusters there and there, on average it should be the same. And we have ways to predict the noise. We can take isotropic samples, simulations, and we can see how intrinsic noise there is, and we can then subtract this noise from the H0 variation. So we do have statistical games to disentangle the two, let's say, yes. But overall, statistically, this should be the same everywhere. Otherwise, it's another way. It's another expression of an anisotropy. Why should thermodynamics be different in different directions? It's another problem. You just mitigate the problem. It's an option. It's a choice to just assume that cosmology is what varies and not local physics, at cluster scales. Right. So, but we can play a different game, and we can also assume that it's not isotropic, right? Standard cosmology. Now, how we could explain the difference of these observables at different directions? Through the redshift. The observed redshift, what we measure is a combination of the cosmological redshift plus the peculiar velocity redshift. And this is what bulk flow means. Again, we'll see it in more detail later on. And we can play around with different bulk flow models to see what's the peculiar velocity redshift one should have at different directions to alleviate any tension. So it's the same effect, just choose to express it as a bulk flow or an H0 anisotropy. But again, as you'll see later on, there are ways to disentangle the two. So small overview, cosmology dependent part for any scale relation. This is the LT, but you can play the same game with any quantities you think of. There is always a cosmological residual. And you can have one sample, have 10 scan relations, get 10 different maps of H0 anisotropy, see if they are consistent, combine the independent data, and have a beautiful constraint at the end.
It's well known that the CMB contains an anisotropy at the level of 10 to the -5.
Yes.
This is irrelevant for what you're computing here.
Yes and no. So in the CMB, we assume that the dipole comes solely from our peculiar velocity motion within the CMB rest frame, right?
Yes, but even if you subtract that, you still have a direction, right?
Well, then you have second order anisotropies, like you have the hemispherical asymmetry, you have things like that. Yeah, these are low signal anisotropies yet, 2, 3 sigma. So for now, not a lot of work has been devoted to that, but we have some relevance for the dipole, because if it's not purely kinematic, if there is an intrinsic anisotropy, then it might correlate with what we'll find later on. But the assumption is that the rest frame of the CMB is perfectly isotropic. We convert everything, we boost everything in the CMB rest frame, our clusters, redshifts, everything in the CMB rest frame. We should see isotropy at 200 megaparsecs. Do we see it or not? That's the question we try to tackle here.
By the way, since you mentioned it, is there a physical process that would change the rest frame today and in the CMB?
Yes, theoretically, yes. But
what would be such a process?
for example, there are these Bianchi universes, which are not they are homogeneous but not isotropic universes. It's a different model of than FRW.
That assumes cosmological evolution.
Right. Within the lambda CDM, no, there is no such process. Except if we are overconfident in the homogeneity scale of lambda CDM in the local universe. But yeah, it's just one can find ways. For example, if sigma 8 varies with scale, for example, and we don't model that, it can create a more clumpy universe locally. So this can create more gravitational attraction, stronger ones at larger scales than we predict. There are ways to mitigate the issue within lambda, or not. I mean, you don't have lambda CDM if you change these things. You have a different model, but a sibling of lambda CDM, or there are ways to just go to different cosmologies completely. So the cluster sample we use, it's 350 of the brightest X-ray clusters in the sky. Since they are the brightest, they are also quite close by. Median redshift of 0.09. You can see the histogram here. We cover the full sky, except for this plane, which we intentionally mask to avoid the galaxy. And if you look at supernova, I have some backup slides. You have 80% of the supernova here, 20% here, nothing here. So that's the big advantage of clusters. They cover the full sky up to much larger redshifts than galaxies, for example. And we measure in our own, because we constructed this sample in our group, we measure the X-ray luminosity, the effective radius, the temperature, the YZ parameter from the Planck maps, and the infrared luminosity of the brightest cluster galaxy for each cluster.
Is there such an anisotropy in the supernova? Is it what we looked?
Yes, exactly. It's supernova are not there all the time, so you have to choose a sky part, focus there like a SDSS, and also because they have mostly ground instruments for surveys, mostly in the northern hemisphere. They don't have good coverage on the southern hemisphere, but it's mostly you have to choose a part. You cannot do all sky survey. But LSST will fix that in a couple of years. We'll have thousands of supernova all over the ground.
When you say the infrared of the brightest galaxy, you refer to too much.
Because we use
stellar mass that you use, or
yes, exactly. It's from the central galaxy of the cluster, so like the BCG.
but when you say you measure the infrared, you must say the 1 to 1,000 microns.
Yes, exactly. Yes, yes. Because the size of the cluster correlates with the size of the central galaxy at the end. So if you know that the central galaxy is bigger, you have a scaling relation that the cluster also is bigger.
So again, so this L, capital L, what luminosity is this?
It's the 2 mass the infrared luminosity. I don't remember the frequency.
Near
exactly.
infrared.
Near infrared, yes.
So it's the stellar mass.
Yes,
luminosity.
yes, yes. Yeah.
Yeah.
Yeah. So it's the radius in which you see 50% of the X-ray emission. It's the isophotal, let's say, radius. So these 5 quantities allow us to build 10 scaling relations, which you can see here. Others are very narrow, others are very noisy. For example, this is the luminosity of the BCG versus the temperature. What we do is study the anisotropy for all of them. Some of them are very sensitive to cosmology. Others are completely insensitive, and they are sensitive on galactic effects. Others are sensitive only to cluster morphology and cluster physics stuff. So having different pieces of the puzzle, we can disentangle the cosmological anisotropy from systematics, from cluster physics. So it's very important to have all of those scaling relations to fully understand what you are seeing and not overestimate your cosmological anisotropy. So we'll move on to the apparent H0 variations. I'll just focus on two relations, the most useful ones, LT and YZ temperature. And you can see that with an H0 change towards the sky, we'll get a shift up and down. We don't get any left and right shift because we have a temperature. So if my scaling relation is here on one part of the sky and here on the other part of the sky, after all the systematic checks, I can conclude that maybe H0 is different in these directions. What we see is this, because it's the PDF, you don't have the color bar, but blue is low, yellow is high. You can see that we get 3 sigma and 4 sigma and a dipole signal from both maps, 9%, 13% anisotropy, and these are nearly independent results. So there is no reason why this should match. The only correlation comes from the temperature. YZ and LX are completely independent. The temperature carries no cosmology. So in terms of cosmology, these are completely independent. There is no reason why this should match. Nevertheless, they do. And they also have very different systematics. For example, you have X-ray absorption here, which of course be correct, but you never know. You don't have X-ray absorption here. You have other kind of stuff. So the fact that they match so nicely, it's very suggestive that something is going on actually. To visualize things a little bit better, we built the first Hubble diagram of clusters. You can see here blue dots come from the blue region, low H0, red dots from the rest of the sky. Even by eye, you can see that the blue dots are systematically higher, which means that for the same redshift, you get higher distance for this region, which can be interpreted as a lower H0. Now, the main result, all that stuff that I saw you are already published, it's the work of my PhD. The main result was to combine everything together, throw everything in one big map, X-ray, microwave, infrared, and also combine with other completely independent cluster samples that they also agree, which is very surprising. Different samples, different cluster populations, different X-ray instruments. Throw everything together in a sophisticated analysis and create the first ever H0 variation map from different wavelengths. And when we do that, we get this map. So again, you have 5, 6, 10 different maps that trace the same thing. If you stack them together, it becomes very smooth. This is an unsmooth image. This is just how it turns out to be. This is a dipole anisotropy, emerges naturally. We didn't force a dipole in our modeling. 9% H0 variation. And again, if you stack together a lot of 3 sigma signals, you get the 5 sigma at the end. And this was not estimated by analytical approaches like chi-square and stuff. We just used mock samples, millions of them. We applied the same statistical approach that we do with the real data. And we saw how frequently we extract what we see in the observed data. It turns out it's 1 in many million cases, which corresponds to 5.4 sigma. And in terms of significance, this is still the most robust evidence for a local anisotropy that we have. Yep.
So when you say the LC effect is completely independent from the luminosity X-rays, it's how confident are you of that?
I mean, yes, I mean the measurement is completely
The
independent.
But
Yes.
the process is not.
The process is not, but we do take into account the scatter. So what happens is that they trace the same thing, right? They trace the gas. One is insensitive to galaxy density squared. The other is, sorry, not galaxy, gas density. The other is sensitive to gas density, that's it. So, and to the temperature. So they have a correlation, a physical correlation, not a measurement correlation on their scatter, which means if I have a fixed temperature and I get an upscattered LX, it's likely, not for sure, but it's likely the correlation coefficient is 0.4 or something, that my YZ will also be upscattered. If I neglect this, I overestimate my anisotropy, but we don't. If I neglect this, I get 6.8 sigma, but we do take that into account and bring it down to 5.4 sigma. So, to come back to that, These are the two papers that we have on the subject. I mean, we have more now, but I mean, what you saw. These are both 40 pages, like 5 pages cosmology, 7 pages cosmology, 35 pages of systematic tests. Because if you find something like that, you cannot just throw it to the public and say, look what we found. You have to be extremely careful of what you claim. So we did a bunch of tests. These are mostly cluster related, but I'm happy to discuss anything you like later on. The end conclusion is that we don't find anything that could alleviate the anisotropy, so it remains what it is.
What is the zone of avoidance?
The zone of avoidance is in the sky distribution I showed, we mask the galactic plane. Now, it happens that the anisotropy is close to the galactic plane. So what if the gap there somehow barriers the direction of the anisotropy and the amplitude? So what we did was create mock samples, full sky, measure anisotropy, mask it, remeasure anisotropy, quantify the bias out of the gap, or create isotropic samples masked and see if we see anisotropies, all these things that we did. We found that there is a bias of like 8–10%, which means maybe our 5.4 sigma is 5 sigma. That's it. So we don't really worry because the cones we use are also very large, so they are not really affected by the cone. Yeah. Yes, the Malmquist bias has to do with the selection of the sample. It's a flux limited sample, right? So if I randomly have a population of more relaxed clusters there, more relaxed clusters are more centrally peaked. They are more luminous intrinsically. So maybe some of them will jump higher than the selection function, and I will detect them. But on the other side, they won't jump higher because they are not as relaxed, out of chance, right? Different cluster populations. And what will happen is that I will see brighter clusters there than there, which I will interpret as higher H not there than there. So we also test that very carefully, but it's completely no issue because we have a homogeneous selection function and hundreds of clusters. So fortunately, everything is consistent. Right. So up to now, I said H not dipoles, all the stuff. It doesn't mean that H not is anisotropic. It means that this is the parameter we chose to project our anisotropy onto, right? But there might be something else. We might have a large bulk flow in an isotropic universe. So to quantify that, we derived the first ever bulk flow constraints from cluster scaling relations. And now I'll just make a small parenthesis to explain what the bulk flow is. So in local scales, we have inhomogeneities, right? We have the galaxies, we have the clusters, we have voids. So us as observers, we are attracted due to gravity towards a nearby supercluster and not towards a void. This creates peculiar velocities all over the place that have nothing to do with cosmic expansion. As we go to larger scales, homogeneity scales, according to lambda CDM, the matter here and here should be pretty much the same, meaning that the observer here, the bulk of the universe here, should not be attracted right or left. It should be, the average peculiar velocity should converge to 0. When it doesn't converge to 0, we call it the bulk flow. What happens is that if I observe clusters in here, the measured redshift is a combination of the cosmological redshift, the Hubble expansion redshift, and the peculiar velocity redshift. If I ignore this, I over or underestimate this, and this bias propagates to my cluster properties. And then I see anisotropies where there are no anisotropies, but there are bulk flows. So we need to test that very carefully. To visualize it again, same slide as before, but now don't think of a shift up and down. Think that for the same distance, you have different redshifts. So the shift is left and right. So that's a bulk flow. Now, whatever we did, we tested different cluster scaling relations, different statistical approaches, different samples, different spheres, different cells. We always found a 900 kilometers per second bulk flow up to 500 megaparsecs, which is highly inconsistent with lambda CDM. And this is an overview of past bulk flow constraints. As you can see at local scales, everything is very consistent, no issue. As we move on towards larger scales, things start to be a little bit problematic than from other surveys. For example, There was the cosmic flows 4 survey, which are like these guys are the standard of bulk flows, right? It's what Adam Rees is for supernova. They are very, very lambda CDM people, let's say. And I'm sure they didn't like the result, but data don't lie. So they found a 5 sigma inconsistency between lambda CDM and their result at 200 megaparsecs. So things start to emerge, problems at these scales. And our result is here, which it might seem that it's inconsistent, but this difference in distance, because this is log scale, it's larger than this difference, right? So in linear scale, our result would be somewhere here. So to me, it looks like a straight line or even an increasing line is a better description from the lambda CDM description. Also, our uncertainty is very large, right? So we are only 2 sigma away from this. But yeah, the issue is that both galaxies and clusters at these scales do not agree with lambda CDM. And it's the only constraint we have up to such large cosmic volumes, and that's the beauty of clusters. They can give you that. Galaxies cannot really go beyond that point. It will take decades to go beyond that point. So clusters are only hope to sample this parameter space here.
This line and flow will already takes into account the silver grade factor and local emissions.
These are very close by. So our cluster sample is much further away than the great attractor and the supply supercluster.
So, but these corrections also oh, I see what you want.
Right, yeah, so they don't really have an effect. Yeah.
Costa, can I ask something? So, how do I interpret the bulk flow kilometers per second exactly? So you measure the velocity of a cluster, let's say that's 500 megaparsecs.
Yes. So each cluster has a deviation from the best fit line. All right. So you attribute this deviation to a peculiar velocity of the cluster. Now you take all clusters within 400 megaparsecs, and you average out these peculiar velocities. And the bulk flow is the average.
So you have a thin spherical shell, let's say, and you pick all of the clusters that line that shell.
Yes, usually it's spheres. We also did the cells as a cross-check, but the bulk flow is defined in spheres.
So it's the cumulative.
Yes. So the larger the scale, the smaller the bulk flow should be.
Yeah.
Because the larger samples you have for the average. And this is the vector average, right? So if I have here and here, the average is 0. Yep.
The other points in that flow that seem to agree are galaxy clusters.
Only galaxies. Clusters, we have the only constraint up to now.
So which point there is a galaxy?
No, these are galaxy samples.
Galaxy.
So yeah, there are thousands and thousands of galaxies, but you cannot measure the stuff you need for galaxies below 200 beyond 200 megaparsecs because they get very faint. Clusters don't get faint. That faint. So these are all galaxy samples of 30 megaparsecs, 60, where we don't have any disagreement with lambda CDM. But the bulk flow doesn't seem to decrease. That's the problem. As you increase the scale, it doesn't seem to drop.
You don't think that's a problem with different methods that
But that's a strength because different methods, different samples, if they give you the same thing, they have different systematics. So it's indicative that systematics is not the reason behind it. If there was only sample one method, then you're more suspicious. Now, all that stuff are already published. So from now on, they are not published. And I want to tell you what we can do to improve our constraints, right? Because we're not satisfied. We want to do better. So there are 3 steps we need to do. First of all, decrease the scatter, get higher sensitivity on H0. Second of all, get rid of the X-ray temperature because we have made like million tests, but maybe there is a systematic in the X-ray temperature. We ignore a direction systematic. We have to use a different cosmology-independent cluster proxy, the galaxy velocity dispersion. Third step, use much larger cluster samples, independent ones, to see what's going on. And these 3 things combined, they give us much better cosmological constraints, as you'll see. So step number 1, higher sensitivity on H0. We measure the gas mass. The gas mass has a dependency on H0 to the power of 5/2. So it's the most cosmological sensitive cluster quantity one can measure. At the same time, this correlation has the lowest scatter on H0. So 2 things at the same time help us get better constraints. But it's not easy to measure, so we only have it for 180 clusters, 180 clusters up to now. We get this map, still 3.6 sigma with a new cluster quantity, 11% H not anisotropy, same as before. The only difference is that the direction is a little bit shifted, but it's only 37 degrees. This corresponds to only half sigma. So statistically, they are completely consistent because the uncertainty in the direction are still all over the place, unfortunately. So test number one, the anisotropies passed the test. Test number two, get rid of the temperature. Use a meta-catalog compiled for Euclid with a velocity dispersion values. We have 320 velocity dispersion. So velocity dispersion is like the optical temperature of the cluster, right? It describes pretty much the kinetic energy of the galaxies within the cluster, and the temperature does the same for the gas. So they are very similar. We study, actually, this is the work of Aditya Pandya, my last bond student. He submitted early August in A&A. So we hope it will get accepted soon. It's a fantastic work. To not spend that much time explaining everything, I'll just say that, as you can see, we get a very similar result with a completely independent cluster proxy, again in optical, at 3.6 sigma, which is amazing because the LX are also different. They are not the ones I used. So again, this is a nearly independent result, which reconfirms what we saw before. And now, in my opinion, maybe the most important result, Rosita. Rosita performs the first all-sky survey in X-rays since 30 years, and the first ever in hard X-rays. And it scans the full sky, but the sky is divided. So Germany has proprietary on the Western Galactic Hemisphere, Russia has proprietary on the Eastern Galactic Hemisphere. So we only have half of the data, half of the sky, but it has already produced the largest cluster sample ever compiled with 12,000 clusters. 8,000 are new discoveries. We didn't know they even exist. So, and we have masses, luminosities, everything for each cluster, gas masses. So it's an amazing volume of new data. And we said, okay, we should test cosmic isotropy with Rosita. Of course, it's also much higher redshift than what we used before. One weakness of Rosita is that the effective area, its sensitivity towards higher energies drops significantly. And as a result, temperature measurements are not easy to obtain. So from the 12,000 clusters, we have good, precise temperature measurements for only 400 and something clusters. But you can test cosmic isotropy, as I said in the beginning, with any quantity you like. So you can use other simulations with thousands of clusters. We just want to make a cross-check with what we saw before. So what you'll see in the next slide is a completely independent result. Different clusters, different telescopes, different people doing the analysis, right? Nothing in similar. And we get exactly the same anisotropy map. So this is the result of two simulations. I was waiting for this map since my master studies for like 5-6 years. And when I ran the CODA, I thought I was still running the old sample, just half the sky. So it's exactly the same map, like I cut it in half. And these are even different clusters. They're not even the same clusters. So that's a 3 sigma result. Why it's only 3 sigma? We have half of the sky, first of all. And second of all, we have much scatter because we are using smaller clusters. The temperatures are not great, but we have a lot of data. But still, 3 sigma alone is nothing, right? If we only have the Rosita, we wouldn't be interested in the 3 sigma. But if you stack this 3 sigma on top of the 5 sigma you saw before, then you get the idea that it's a huge result. And the agreement on H naught on direction is really mind-blowing. So in terms of bulk flow, we get a similar bulk flow, quite uncertain. One thing actually I forgot to summarize before. It's a project we do in Leiden. All that 5 sigma, 3 sigma, all that stuff, they refer to the dipole of H naught. They don't refer to the tension with lambda CDM. Maybe in lambda CDM, for our cluster redshift distribution, maybe lambda CDM still allows for a 4-5%. It's not an isotropy at these scales, right? Because we're not at 5 gigaparsecs. So we don't still know the true tension with lambda CDM. We can use cosmological simulations to find out. So we apply everything we applied in the real data, we apply it in isotropic cosmological simulations, and we see how frequently we retrieve what we see in the real data. So Flamingo, let me say they are the most state-of-the-art, best hydrodynamical cosmological simulations out there. They have 2 orders of magnitude better particle resolution than the previous state-of-the-art simulation, so 10 to the 9 solar masses. They have volumes of 22 cubed gigaparsecs and full cluster physics, full baryonic physics. So everything we have for the real data, we have for millions of clusters in Flamingo as well. And we create light cones for different observers, and we see what kind of anisotropies do we get. This is also the work for a master student who is really brilliant. In Leiden, you have to do 2 master theses, 1 per year. This is his first master thesis, and he's already writing a paper that we plan to submit mid-September on that. So yeah, it's his name is Yujie He from China. He's really brilliant. So as a proof of how Flamingo is similar with observations, this is after the cluster selection and everything we do. This is the redshift distribution we get, which is extremely similar to our real data. And this is what they found for the 2 first light cones. Right now, the code runs for 10,000 light cones in order to have better statistics. And what we see is that H0 seems to vary 4%, 3.6%. And these are not dipoles, these are just the maximum and minimum nodes. So if you force a dipole, as we see in the data, this gets at 3, and this gets at 2%. What does this tell us? It tells us that either lambda CDM randomly allows such dipoles at these scales, or our methodology, and that's what we want to test, our methodology probably slightly overestimates the anisotropy. And we understand why. I'm not going to bore you with that. It has to do with the scatter to skin relation. But now we know how much of an overestimate we had in the real data. So in reality, after we correct for that, our 9% dipole in H0 becomes 6%, but 6% clear, pure dipole, no noise or anything. And our tension of lambda CDM is 3.8 sigma, but this is the tension of the published results of my PhD. It's not the tension of the new work with the gas mass, with the Rosita, with the velocity dispersion. If you add all that stuff, it rockets. So this brings me to the last part of my talk, which is very brief, like 5 more minutes, and that's it. What we can do in the future, how we will improve in terms of cluster statistics, our work. First subsection, let's say, it's just 1 or 2 slides. It's the X-ray and SZ samples. Firstly, in our sample, we want to increase the gas mass measurements. We also want to put clusters here in the zone of avoidance, not have this gap as we talked before. And we have a successful XMM proposal for that actually. So we do have data now here, and we'll see adding 10% of clusters here compared to the full sample in the correct direction if the signal gets higher or lower. The most important thing is to improve our modeling. So in each cluster, we have so much data to play with. We have the relaxation state, we have the metallicities, we have the concentration, we have a lot of stuff. So we have to see what kind of parameters we should use to improve the modeling, to reduce the scatter. As you can see, we have already done that. By reducing the scatter, you improve your uncertainties. Reducing the scatter and improving the modeling is better than getting like 3 times more clusters than you have already. It's more important. Rosita, besides what I told you already, they have a lot of velocity dispersion measurements. So we are going to use this to use new skin relations. And the results you saw are only from the first all-sky survey. We have 3 more coming with 40,000 clusters. These numbers are out of reality for 3-4 years ago, where we had like 800 clusters in total. And we also have other samples like X-class, which is a collaboration of all over Europe. For example, me, Ilias Blouridis from Athens, Nicolas Clerc from Lyon. We have a project called X-class, where we measure temperatures for more than 600 clusters above redshift 0.2. We're going to understand if we see bulk flows in the local universe or not using X-class. And then you have SZ surveys. You have the Atacama Cosmology Telescope, 4,000 clusters. You have new Planck cluster subs coming out this month, actually this week even, with more than 1,000 clusters. So we have we have a variety of data to play with in order to improve our results. And the final thing is the optical monsters that are coming. For example, Euclid, where you have a lot of scatter. In optical scaling relations, you have a lot of scatter, but you have a mind-blowing number of clusters, like 100,000 massive clusters coming out from Euclid, from these blue sky areas. A lot of them will have velocity dispersion, richness, but velocity dispersion is not something that Euclid will thrive upon. So we need follow-up observations. And Migkas, for example, can provide us with follow-up measurements of Euclid clusters on the velocity dispersion, which will be very helpful to build more scaling relations. You have Daisy, you have Rubin, you have hundreds of thousands of clusters coming in the next few years, which will allow for an unprecedented analysis on cosmic and anisotropy clusters. This brings me to my summary. So I hope I convinced you that galaxy clusters are extremely useful to test these kind of things, which are crucial for understanding cosmology. And when we do so, we find 5 sigma anisotropy in H not dipole, 9%. Now we know that it's 6 or 6.5%. Huge bulk flow, both inconsistent with lambda CDM. And new independent measurements confirm the previous picture we had for the local universe. Zeta completely independently confirms what we thought we knew before. Flamingo simulations reassure us that our methodology works, and the optical, as I said, monsters are coming in, Euclid, Daisy, Rubin, LSST, to provide us with huge volumes of data. And yeah, we'll have much more interesting answers very soon, in the next 4 or 5 years or so. So thank you.
Thank you, Costa. Questions?
Sorry, maybe you mentioned it at the beginning, but I wasn't paying attention.
Thank you.
At the very beginning. Can it be confirmed, or has it been done with the supernova?
Yeah. So what I was saying before, this is not the latest, but the second to latest supernova sample. This is the current situation with supernova samples. You see how many supernova you have here, and you see where we find an anisotropy. So it happens so that we don't have any supernova data there. In the future, LSST will cover much larger parts of the sky, and we are expecting to have maybe 10, 20,000 supernova type 1A covering this region as well, not uniformly, but covering big parts of this region in the next 6, 7 years, maybe. So for now, we cannot do any significant work with supernova. In the next 6 years, we will be able to do that, yes, and combining them two.
So it could be the origin of the.
I think they are not separate problems. The Hubble tension says that H naught is larger from supernova, but if you see where supernova lie, and if you project these data points here, and you make the average, you see that H naught is overestimated by a few percent. It wouldn't solve the Hubble tension if this is true.
Yeah.
It wouldn't solve it, but from 74, H naught from supernova would bring it down to 70 or so. Then this 5, 6 sigma becomes 3 sigma. Maybe it's there, but I think it's overestimated, the significance.
Can you please plot your results from the Zeta?
Yes.
Yeah.
Okay, yeah.
Not this one, the other one actually, where you have the fit to the data.
Right, yeah. It's here.
So here, right?
Yeah.
So your H naught of 62.1 plus minus 2.2. Okay, I understand you cannot be certain about actual values of H naught.
Yes.
But this could be the same as the CMB.
Yes.
Very similar to the Planck result.
Yes.
And then we get to 73.
Yes.
But on the other side, where you, I mean, on the left now side of your previous results, it's a orange one. So H naught is probably similar to the CMB, but the supernovae find 73.
On the other side,
Yeah, so you have now an agreement with the supernova.
well,
In the same area where they measure their H naught, you measure a smaller value than what they do.
no. Here, if you see the other map, so here the 73 comes from from the rest of this area. So we
It's
have
the rest,
it's the
so,
rest.
so it's there that you find, it's in the blue that you find the 60.
Yes,
So you are in agreement with the
Yes.
supernovae?
yes,
All right, okay, fine. So when LSST will come,
Mhm.
if they do not find now 62,
yes,
would that be a problem with you? I mean,
yes,
so
but
would you expect your results, would you expect LSST to show the same kind of dipole?
I do actually, I
you
do, yes.
So if LSST doesn't show that,
Yeah, then that's science. We have to find what's going on.
so it has to be something with the clusters, whatever.
No, maybe something with a supernovae for the simple reason that clusters say the same thing for any cluster sample you choose, any observable, any telescope. So there is a huge consistency between different. So we haven't found the cluster sample yet that doesn't show this. That's the issue.
Fine, so.
But
So that would be interesting.
62 here, Rosita has a lot of scatter. So this 62 in the original maps, the robust maps, we have 67. So this 62 is probably plus minus 3. So
67 is
67.
even closer to the plus.
yes, yes, exactly, exactly. But it's only with this, it's this region of the dipole.
Yeah, yeah, I agree. So suppose everything is correct in your analysis and there is the real
Yeah.
change. So how can you explain this simply? The fact that it's so isotropic. So what happens between, 300,000 years after Big Bang and
Yeah.
nowadays?
Yeah.
What
So,
happens? I mean, what?
That's a great question. That's what we need to tackle. But first,
Things that, are there any ideas? Are there any?
not from me.
No.
Yeah, I know.
There are many people.
There are many people that actually try to solve the Hubble tension now using that kind of stuff, like the early dark energy stuff. So things that, or sigmoid evolution, things that might make the universe more clumpy than we think from CMB. As a result, we have more inhomogeneity at 500 megaparsecs. And as a result, these are all peculiar velocities in an isotropic universe, which suggests that the lambda CDM needs a fix somewhere, like an extra evolution. Now, in my opinion, it gets to a point that you just add epicycles over epicycles over epicycles.
That's the problem now. Could it be that it's all wrong? I mean, lambda CDM is all wrong.
So I was in a
Lambda, for
conference.
example.
I was in a conference in London in April with James Peebles and George Stachel and Wendy Friedman. They were discussing all that. So Peebles is convinced that it's all wrong, but it's a very good approximation of reality. So as we get better and better data, we deviate from the approximation. While our uncertainty is big, lambda CDM fits greatly. But it may be an approximation, and it's like whatever cosmological model we built for the last 3,000 years, it was all wrong. Why lambda CDM should be the last, right? I think there is an improvement coming on soon.
Was this conference the Royal Society meeting?
Yes.
What do you say about the work of Sudhir Sarkar?
Right. So they trace a different kind of anisotropy. They trace redshifts above 0.1 with quasars. They have a very robust argument, and it might be that if we have clusters at 0.6, 0.8, 1, we keep seeing this dipole, which would mean that the matter rest frame is different from the radiation rest frame, which is very confusing. But if the data suggests that, but okay, Subir is a little bit overwhelming sometimes, but it doesn't change the fact that their analysis has been tested all over again. They have been cross-checked by other groups, and the dipole is there all the time. So
I have 3 questions. Are your dipole, is it aligned with Konstantinos dipole?
no, but it's completely different cosmic scales.
Okay.
Completely.
Well, that's my first question. The second question, is your dipole aligned with the CMB dipole,
The CMB dipole is completely aligned with Sarkar's dipole.
but not yours?
No, it's like here. It's not 180 degrees. It's something like 60 degrees away. So we
Well,
are.
the CMB dipole is aligned with the quadrupole, the octapole, it's the axis of Eden kind of thing.
Yes, yes.
So, and this is aligned with the larger scales that
Much larger.
quasars
Yes.
find, but not your cluster.
No, because we're at 0.1 redshift.
Very interesting.
So my belief, my personal belief, I cannot prove it, is that, okay, the uncertainties do not exclude any explanation. But my belief is that we are looking not in a universal anisotropy. We look at a very large bulk flow that shouldn't be there in lambda CDM.
Okay.
I don't know if I don't know if clusters will show the same dipole if we go at much larger scales.
So it's not just, so in a sense, right, if you go from, if you start from the CMB and you come all the way to today, you see that the anisotropy is not just growing in one direction, but it's also twisting.
Yes, so it depends on where you start. If you start from the CMB, the anisotropy is here, 364 kilometers for it's not Subir's work, right? He's the PI, but it's also the work. But if you take their result, the peculiar velocity compared to the quasar strain is 900 kilometers per second. It's exactly the value we derive. So what happens is at redshift 2, it starts here, and then it goes at the same amplitude at redshift 0.1 here.
So it's twisting.
Yeah, this.
Wow.
But again, my belief is that it's also a local effect, what we see here, due to the inhomogeneity of the matter distribution. So if we had clusters at 0.6, 0.7, maybe we would see the anisotropy here.
Align, yeah, go back to.
Maybe, I don't know, that's just a belief.
Okay, my last question. You insisted that the temperature and the velocity dispersion of galaxies in clusters are measures independent of cosmology.
Yes.
But both of those values, right, are basically measures of the depth of the gravitational potential.
Yes.
So what if there is, I mean, the clusters are mildly nonlinear objects, right? They are not highly nonlinear objects, so they are barely virialized, right? So what if this anisotropy is an imprint of this early sigma A anisotropy or something? I mean,
that's a great question. So we have discussed that extensively. So what I meant with the cosmology independent is that they don't depend on the redshift distance relation. But they do depend on the cluster evolution, which does depend on cosmology. Mostly depends on omega matter, stuff like that. In our appendix in 2020, we have quantified how much this would change, let's say, our temperature, luminosity temperature relation, if cluster evolution changed, right? So there is an effect, but it's much smaller than the current noise we have. So it makes no sense to correct it right now, because if we have 9%, for example, anisotropy, it's a 0.5% effect. As we go to precision cluster anisotropy tests, we do need to take that into account. Not for H naught, but if we go at higher redshifts and want to test omega matter, sigma 8, omega lambda, then we need to take the cluster evolution thing into account.
As your samples increase, can't you now do this kind of samples at the same redshift? Because you have lots of samples, so now you can have both sides the same redshift clusters.
Yes.
So now there is no evolution effect, right?
Right,
Same
exactly.
redshift.
I mean, there is an evolution effect with a direction. So, yes.
If it is the same redshift.
Right. So
Yeah.
this is what this is what
Okay, that could be some scatter.
Also.
right.
I think either it's bar flow or it's H naught.
So that's exactly what we did with the redshift cells. It's sorry, yeah. So
This is redshift.
these are cells.
You did it already.
Yes,
Ah.
we don't see the dipole converging to zero. I mean, okay, here the other side.
Yes. Oh, wow.
But what Kostas, I think, suggested is that if there is an intrinsic cosmological anisotropy and sigma 8 is different, then changes cluster evolution for the same redshift, left and right. So we don't account for that up to now because it's a minimal effect compared to our noise. But in the future, we need to take that.
Right. So if we take into account this bottom figure, we should actually attribute this anisotropy to bulk flow, not with different, expansion rates.
So for now, we cannot tell them apart because they have the same effect on the scan relations at this red. So here, you cannot say if it's up and down or left and right.
Yeah.
But if we go at higher redshifts, H naught does the causes the same change despite the redshift. So 0.7 redshift, you'll see the same up and down. But at 0.7 or 0.6 or 0.5, if you have a bulk flow, the peculiar velocity is irrelevant compared to the Hubble expansion velocity. So bulk flows should make no change, should cause no anisotropy above 0.4, 0.5. H naught will cause the same anisotropy as here. So the answer is we need clusters here to understand what's going on.
Yeah, but I'm shifting more towards bulk flow because you have the other points in the figure before with galaxies and other stuff and
Right.
quasars from Sakar's group.
You don't know, yes, but
Or
here-
have they focused specifically to bulk flow?
here you can also not tell if it's H naught or bulk flow, but it's a more conventional expression, let's say, and more conservative to say that it's a bulk flow. Different H naught, a little bit more problematic, more provocative than a bulk flow.
All right, well, Kostas is here tomorrow and the day after, he's
Yeah.
in 246. So let's thank him once more.